Hi, good morning all. So today we are going to start a new topic, approximation methods in quantum mechanics. So as we know that the solving of quantum mechanics problem is basically solving of Schrodinger equation, and it is rather very difficult to solve Schrodinger equation in many problems. So an algebraic method, a direct method of solving differential equation is not very straightforward. Okay, so then we have to use certain approximation methods to find the solution of Schrodinger equation. So there are many approximation methods like time dependent perturbation theory, time independent perturbation theory, WKB approximation, the variation method. So there are many methods, many approximation methods available in quantum mechanics. So certain methods would be applicable for certain kind of problems. Okay, so there is no one solution there is only one approximation for all problems. Okay, so we have to apply the approximation methods based on the problem. So today I am going to discuss a new method called WKB approximation. This WKB is come from three physicists, Wenzel, Kramer and Bloch. This is what is called WKB. Okay, so this is the secret behind this name, the WKB approximation. So WKB approximation is in the name of these three famous scientists, Wenzel, Kramer and Bloch. Okay, now we can directly go to what is this approximation. Okay, now this approximation is valid only for one dimension problem. Not only one dimension, one dimensional time independent problems. Okay, that is, the WKB approximation is not valid for time dependent problems. So it is valid only for time independent problem. Okay, and moreover it is one dimensional, but that is not a much issue. So if you have three dimensional also, it is possible to divide a three dimensional problem into three one dimensional problem, that as we seen while discussing the harmonic oscillator problem. The harmonic oscillator problem we have solved for one dimension, but it is applicable, it is possible to solve the harmonic oscillator problem for higher dimension as well by changing the two-dimensional harmonic oscillator as two one-dimensional harmonic oscillator. Okay, so although it is applicable for one dimension, but it is for some system we can apply for even higher dimension as well. Okay, now what is this approximation? So before going to approximation, we have to know the form of wave function for normal time independent problems. Okay, so consider a system with potential V of x equal to V, which is a constant. So then Schrodinger equation for one dimensional problem, the Schrodinger equation I can write as minus h bar square by 2m v square psi of x by dx square plus v the psi of x equal to v psi of x. So if you rewrite, you can write this as v square psi of x by dx square equals 2m by h bar square v minus e into psi x, or you can write the same thing as v square psi by dx square equal to minus some k square into psi of x, where k square is 2m by h bar square e minus e. Okay. Now what is the solution for this particular equation? D square psi by dx square gives minus k square psi of x. The possible solutions are the harmonic functions e raised to ikx or e raised to minus ikx. So a general solution for a wave function psi of x, I can write some k into e raised to plus or minus ikx. Okay, so this is a real solution. Okay, the actual solution for a one-dimensional problem with a constant potential. So if you have a constant potential, then the wave function I can write a into e raised to plus or minus I kx. Now what is k here? K square is 2m by h bar square e minus v, and if you look at k, that will be equal to square root of 2m into e minus v divided by h square. Now recall, now here E is the total energy and V is the potential. So if the total energy is greater than the potential, then K would be a real number, and if E is less than V, the K would be an imaginary number. Okay. So for energy greater than the potential, the wave function I can write K into e raised to plus or minus I kx, where K is real. And for the energy less than potential, is it possible? Can the system has the total energy less than the potential energy? In classical mechanics, such condition is not possible, but it is allowed in quantum mechanics. So E less than V, we can call it as a classically formula. Because we know that the total energy is a sum of kinetic and potential. Okay. So if the total energy is less than potential energy, that means the kinetic energy should become negative. So classically that is not possible. The kinetic energy cannot be negative in classical mechanics. So classically the total energy of the system cannot be less than the potential energy of the system. But quantum mechanically that is possible, that is permissible. So that is the beautiful result of quantum mechanics. The particle can exist with the total energy lesser than its potential energy. Okay. Now in such cases, if the energy is less than V, then K becomes imaginary. Okay. So if E less than V, I can get K equal to some I into kappa, where kappa is a real quantity. What would be kappa here? The kappa would be root of 2m V minus E by h cross. Okay. So kappa I can write root of 2m V minus E by h cross. So then I can write my psi of x, that will take the form k into e raised to plus or minus kx. So that means if for the energy less than V, that is the classically forbidden region, the wave function will become exponential. And then the classically permissible region, this is classically permissible. So this is allowed region, classically allowed. So in the classically allowed region, the wave function will become harmonic, and here the wave function is exponential. And this kappa, not k, kappa, and this is exponential. Till now I have not made any approximations. Okay, so what I have done is I have just solved a one dimension time independent Schrodinger equation for constant potential. Okay, so you have to remember this. What I have done till now is I have solved one dimensional time independent Schrodinger equation for constant potential, and for constant potential I have got two cases. One is the total energy greater than the potential energy, the wave function will become harmonic in nature, and the other case is the total energy less than the potential energy. In that case, the wave function will become exponential. It can be positive exponential or negative exponential, that depending upon the boundary conditions of the problem. Okay. Now next we can introduce what is WKB approximation. Okay. So next we can discuss what is actually the WKB approximation is. Okay. Now in the previous session what we have discussed is we have discussed the problem of a constant potential. So if you have a constant potential, if V of x equal to V, then the wave function can take the form either e in plus or minus ikx for energy greater than V, or A in e raised to plus or minus kappa x for energy less than V. Okay. Now what happens if the potential is not a constant? Okay, so if V of x is not a constant, if V of x is not a constant, but if it is a slowly varying function, then the wave function will have the same form. Okay, so if V of x is not a constant, then I cannot use this equation directly. I cannot have the wave function of this form. But we can still use this form if the potential is an almost constant. Okay, so if V of x is not a constant, but if it varies slowly, so very slowly means it should be compared to something else. So if it's very slowly compared to the value of 1 by k. So remember, k is a wave vector. Okay, so 1 by k corresponding to wavelength. So if the potential V of x varies very slowly compared to the de Broglie wavelength of the system, so 1 by k, now in this problem it is 1 by kappa. 1 by kappa. Then the wave function takes the same form as the potential constant, but with one difference. Not one difference, with two differences. And difference are, it will have a varying amplitude and a varying wavelength. Then the wave function takes the above form with varying k or varying kappa and varying amplitude. So A would become function of x and k become kappa and k become function of x. So that means I will write here. So if V of x is slowly varying, if V of x is slowly varying compared to k, then the wave function will take the form some V of x into e raised to plus or minus I k of x into x for energy greater than V, or it can be A of x e raised to plus or minus kappa of x into x for energy division. This is what is called the WKB approximation. Okay, so this is an approximation. This is not the actual solution. It is an approximation. So actually we get this form only for constant potential. But if you are not having a constant potential, rather you have a slowly varying potential, then the wave function can still take the almost same mathematical structure, but with a varying amplitude and a varying wavelength. So that is what is called the WKB approximation. Okay. Now this approximation is valid in classically forbidden region and classically allowed region. Okay. So for E less than V it is applicable, for E greater than V also it is applicable. But it is not applicable at one point. That point is when E approximately equal to V. Such points are called turning points, classically turning points. Okay. Now this approximation is not valid for if energy approximately equal to. Okay. So in order to understand this problem, so these such points are called turning points. So consider a graph. The potential V of x and x, and the V of x suppose is a slowly varying function. Okay, and the total energy, suppose the total energy is this. Now if here you have 2 points x1 and x2 in which the potential and the total energy are same, those points are called the classical turning points. Why this is called turning point? Because classically the particle cannot cross this region. Classically the particle is bounded within x1 and x2, because classically the total energy cannot be lesser than the potential energy. So for the region x greater than x2, the potential is greater than the total energy. So this is a classically forbidden region. And this region also classically forbidden, and between x1 and x2 is the allowed region, the classically allowed region. Okay, so classically the particle should come back after reaching x2. It cannot cross x2. Classically the particle cannot cross a point x1 and x2. It should be within the x1 and x2. So therefore the classical system for this particular potential energy should have a bound state. So it will be bounded within x1 and x2. Okay, but quantum mechanically the particle can exist for the position greater than x2 and beyond x1. There is no issue. Okay, so therefore we have a classically allowed region, classically forbidden region. In all these regions, this wave function is applicable provided if the potential is a slowly varying function. So this WKB approximation is valid for both regions, but except at this particular points. So at the point x1 and at the point x2, that is in the vicinity of x1 and x2, this approximation is not valid. So this is the most difficult part of this problem, the WKB approximation problem. So if you have to deal with such points, the classical turning points, the WKB approximation will be very difficult. If you don't have any such turning points, then there is no issue. We can easily use WKB approximation. Okay. So this is the main issue of the WKB, the dealing of the turning points. Okay. So the dealing of turning points is a very important problem. So for that there are techniques, that is how to deal the wave function around the turning points. Okay, so that we will discuss later. So this is the basic WKB approximation. So if you have a constant potential, this we already see the wave function would be either harmonic function or an exponential function. Okay. Now for normally, if the potential is varying function, if the potential is a function of position, then we cannot use the same wave function. But the WKB says that if the function is a slowly varying function, if the potential is a slowly varying function, okay, slowly varying compared to the d probability wavelength compared to lambda, then we can still use the same form but with the varying amplitude and the varying k. For a region energy greater than V, the wave function will take this form, the harmonic function, the same harmonic function. For the classically forbidden region, it would be an exponential function, but the k and a would be a function of position. Now both this k and a must also be slowly varying, because the potential is slowly varying function. So therefore both k and a must be slowly varying. Okay. And the last thing is, this is not be valid. It is not valid at the vicinity of turning point. So why it is not valid? Because at the turning point, what happens is, if you look at k, the k becomes 0 or kappa becomes 0, because k is root of 2m e minus v by x squared. So when e is approximately v or when e equal to v, the k becomes 0. So at those points, the de Broglie variance will go up to infinity. Okay, so at that point or in that condition, that is around the turning points, this approximation is not valid because I cannot say now the potential is slowly varying if the lambda itself is going up to infinity. Okay, so this statement is not valid around the turning point. So that is why WKB approximation is not valid around the turning points, but it is valid in both the regions of the classically allowed region and classically forbidden region. Okay, so we are stopping here now. In the next session, we will discuss about the general formalism of WKB approximation. Thank you.